Hello everybody and welcome to our OSPF deep dive. I'm thrilled that you chose to join part of your Black Friday with us. We've been doing this, I was trying to think, maybe 6-7 years, but the day after Thanksgiving here in the US, we always go live for a marathon training event teaching a different topic each year. I thought this time we would just take care of OSPF, and what I mean by that is I want to cover with you today every OSPF topic on Cisco's CCNA exam blueprint, the ENCOR exam blueprint, and the ENARSI exam blueprint. Now that's a tall order, so you might be wondering, how long is this going to take? And the answer is I don't really know. My guess, this is a rough guess, because I know some people have asked, but my guess is about 3 hours. Could be a little bit less, could be a little bit more. We'll see. But that's my guess at this point, that we're looking at about 3 hours. Here's what's coming up specifically today. I've had some questions saying, I'm kind of new to this. Are we going to start at the basics? Do I have to have some experience? And the great news is, let me mute one of my monitors over here where I can hear myself. That's not good. All right. We are going to be having a replay of this, which is good news, but it's probably going to be posted tomorrow, and it's going to be missing a few things. Now, if you're joining us live, then you're going to be able to benefit from what we do every Black Friday, and that is give you our biggest discounts on our training products of the entire year. And I've got some special surprises for those of you that stick around to the end of the webcast, so I encourage you to do that. But we are going to start off with the basic theory, and then we're going to talk about how a couple of OSPF routers form neighborships. And there's a difference, by the way, between a neighborship and an adjacency, and we'll be talking about that. We're also going to see that we can have some routers that get a special job in the network. They're called a designated router. We'll see why they help us out and how one gets elected to be a designated router and what happens if it goes down. We'll talk about how an OSPF network can be grouped into different areas they're going to be called. And then we'll take a look at some network types. Now remember, we're going after topics on the CCNA, the ENCOR, and the ENARSI exams. And one of the big topics, especially on the ENARSI exam and a little bit on the CCNA exam, network types. So we'll be dissecting those network types. And I'm going to try to do the impossible today. And that is to simplify LSAs. And that's one of the most intimidating topics, it seems like, from a lot of students out there. Just getting the concept of LSAs is kind of tough. I'm going to try to break it down and super simplify it for you today. We'll talk about timers. That might not sound like anything super impressive, but they're very different than EIGRP timers, and most people don't understand the difference. They think they're the same, and they are definitely not the same. We'll talk about how OSPF does its metric calculation, and we don't like it. By default, so many network administrators out there, they've got a false sense of assurance that they set up OSPF and it just works. It's giving us the best possible path to get from point A to point B. I've got gig links, I've got 10 gig links, I've got fast Ethernet links. It's going to pick the best link. Not by default. By default, it is not going to do that. So I want to make sure that we learn how to optimize that default configuration. Then we're going to be talking about just a basic configuration, starting at the basics again with OSPF version 2. You might want to make a note of this right up front. We're going to be talking today about version 2 of OSPF and version 3. Version 2 only supports IP version 4. Only supports IP version 4. We can support IP version 6 if we go to OSPF version 3, and I'll be setting both of those up for you today. We'll take a look, once we get the basics down, we'll see how we can filter routes, because as we're going from one autonomous system, maybe a couple of businesses merge. This business was running EIGRP, this other business was running OSPF, and they merge all of a sudden. We may not want all of those EIGRP routes coming into our OSPF autonomous system. We'll see how to prevent that. And there are 3 different ways of doing route filtering. We'll talk about all of those today. And to reduce the size of our routing tables, we'll talk about route summarization, and we'll see how if we do have that company merger and we've got an area that's not adjacent to area 0, we'll talk about why that's a deal. We'll see how to fix it. We'll see a workaround. Then we're going to get into some OSPF version 3 configuration to support IP version 6. There's a traditional way of doing it, and that's where you set up OSPF version 2 for IPv4, and you set up OSPF v3 for IPv6. But then we'll say, here's a better way. Here's an address families configuration approach, and that is going to allow us to have one hierarchical structure that does both. It does both OSPF, or rather it does both IP version 4 and IP version 6. And we're going to wrap things up with authentication today. Authentication between a couple of routers and authentication between all the routers in an area. And out in the live interface, I'll be doing lots of demonstrations for you throughout. We'll be talking about commands we can give to troubleshoot some things that might go wrong, how to recognize what goes wrong. So we're integrating a troubleshooting discussion in with all of this. Now, if you're not familiar with me, if you just sort of saw me browsing through YouTube, here's my super quick bio. My name again is Kevin Wallace. I got a couple of CCIEs, one in enterprise infrastructure, one in collaboration. I got my first CCIE back in 2001, so I just passed my 20-year anniversary, which I'm really excited about. And I've been working with Cisco gear since the very first Cisco router out there, the old Cisco AGS Plus router, if anybody remembers that one. And I taught courses for Cisco Learning Partners for about 14 years. And then back in 2014, I decided to just start doing this full time. So I created my own company, Kevin Wallace Training, and we create on-demand IT training courses, and we do live courses as well. I used to work at Walt Disney World, where I was a network designer. My family and I, we are huge Disney fans, and if you attend many of my sessions, I'll tell you a lot of stories from my time down at Disney World. Wrote a bunch of books, done a bunch of video courses for the folks over at Cisco Press. I was honored to get the Distinguished Speaker Award a couple of times at Cisco Live. Bottom line is, I love this stuff. That's enough about me. I love this stuff. I am passionate about it. I am ready to get into it if you are. So we've got 3 different sections today. Let's dive into the first section right now with just an overview of some theory and terminology surrounding OSPF. And the first thing I want you to know about OSPF is it's an open standard, and as a result, I think it's probably the most widely deployed, based on my surveys of my students for years, it's the most widely deployed IGP, an interior gateway protocol. Now, I saw somebody earlier type in this OSPF session, they said, BGP is king. Yeah, it is king of the internet, but that's an exterior gateway protocol. So let's do a survey right now. We've got like 600 people joining us on different platforms. So I don't want you to give away any company secrets, but if you don't mind sharing, can you just type in what IGP, what interior gateway protocol do you run in your company? Let's just kind of do a survey of the group here. It might, don't put BGP because unless you're using iBGP, but for most people, it's going to be OSPF, ISIS, EIGRP, RIP even. So let's see what everybody's saying. We've got a lot of votes for, let's see, OSPF. OSPF wins anytime somebody is saying, scrolling down, oh, somebody using EIGRP and OSPF. Somebody using OSPF and ISIS. That might be in your data centers, my guess. ISIS only. Mixtures of EIGRP and OSPF. Awesome, awesome. Well, that pretty much confirms what I was thinking. It is an open standard, and it is widely deployed, and it's considered to be a link state routing protocol. Now, real quick, what does that mean? It means it has a map of the network. I'm going to get more into that just in a few moments, but think about EIGRP or RIP. RIP is called a distance vector routing protocol, and EIGRP is an advanced distance vector routing protocol. Oh, what's a vector? You remember that from high school? A vector gives you 2 pieces of information. It gives you magnitude and direction. In other words, how far is it to the destination, and which way do I go? What's my direction? You see, EIGRP, as great as it is, I love EIGRP. When I worked at Disney, we had over 500 routers running EIGRP. But EIGRP doesn't have a map of the network. One router doesn't know how everything else is interconnected. OSPF does, because it's a link state routing protocol. And it stores that map in what's called a link state database. And we're going to be seeing that link state database today. And once it gets all that information in the link state database, this router says, I want to get to this network out there. It's going to run an algorithm called the Dijkstra algorithm. It's called the Dijkstra shortest path first algorithm, and it's going to give you the most efficient path to get to that destination network. Now, when I say most efficient, what makes it most efficient? Bandwidth, cost. We're going to use a metric of cost, and the lower cost link is going to win, or the lower cost path is going to win, and higher speed links are going to have lower cost than lower speed links. We'll talk a lot more about that coming up today. But it's not the only link state routing protocol out there. Several people said they were using intermediate system to intermediate system, ISIS. That's the other popular link state routing protocol out there, where every router has a map of the network. Think of your car's navigation system, or even on your smartphone, you've got Google Maps, perhaps, or Apple Maps. When you're saying, give me directions to this location, that's what it's doing. It's running the Dijkstra algorithm on this map of the network that you have. And the metaphor that I often give my students is that OSPF is a lot like working a puzzle. For example, I grabbed one of my family's puzzles. Now, I'm not a big puzzle person, by the way, but my wife and my daughters, they're much more fans of puzzles than I am. But here's the thing I want you to understand about puzzles. With puzzles, we've got all these different puzzle pieces here. And if you and I and a couple of friends were sitting around a table, we would each have a collection of puzzle pieces in front of us. In other words, we would each have a portion of the complete picture. Now, this was, it looks like this one's going to make a family of snowmen is what this one's going to do. But we would each have a picture or a portion of that family of snowmen in these puzzle pieces. That's what OSPF routers are really doing. An OSPF router is going to know about pieces of the network, what it's connected to, for example, and what kind of links it's connected to. And these puzzle pieces are pieces of information that it's going to share with everybody else within the area. And by putting all those puzzle pieces together, that's how these routers collaborate and they build a map of the network. And everybody in that area shares the same map. And if I'm working on a corner over here, or I'm trying to get the stovetop pipe or the stovetop hat on the snowman, I might say, hey, I'm missing the little holly leaf up here. Does anybody have that? And somebody might say, oh yeah, I've got that. And they can provide me a missing piece. Well, routers do that too. They're going to be able to say, I'm missing a certain piece of my topology or my link state database. Can anybody provide it? We'll take a look at the exact message type that's going to ask for that. And a neighbor can say, yeah, I got that piece. Here it is. But the idea is everybody has pieces of information. They're going to be able to share that, and they're going to be able to build this map. Then we're going to run that Dijkstra algorithm to determine the shortest way to get from point A to point B. And when one router is talking to another router and they're sharing their puzzle pieces, by the way, in your notes, you might want to write down that those pieces of information that I'm referring to, they're called LSAs, link state advertisements. Routers that share that information are called adjacencies. As we're about to see, there's a different relationship that routers could have, and that's being neighbors. There's a difference between a neighbor and an adjacency. We'll talk about that. But we're going to be sending these LSAs throughout an area, and we're going to be able to build a map for the area. And that map, we said, is going to be in a link state database. We're going to run that Dijkstra algorithm on it. Now, here's the big point I want you to understand on this slide. Once OSPF says, all right, I have determined the optimal route to get here and here and here and here, just because OSPF has determined what it considers to be the best path to this network, is that any guarantee that the router is going to use that? No. Can somebody tell me? Chat it in. If OSPF says the best way to get to 10.1.1.0/24 is to go to this next top router, but the router running OSPF says, nah, I'm going to go this way instead. What would make a router override what OSPF said was the best way to get there. Anybody have an idea? Go ahead and chat it in if you would. Yeah, administrative distance. Yeah, a lot of people saying, yeah, Rami Network King. A lot of people saying it is administrative distance. That is the believability of routing information. Now, OSPF has an administrative distance of 110. And the lower the AD, the lower the administrative distance, the more believable that routing source. Now, if a network is directly connected to my router, you don't get more believable than being connected to me. So that's going to give you the ultimate administrative distance of a 0. Now, if I, as an administrator, go in and say, well, I want to statically configure a route that's going to override any routing protocol, by default, that's going to have an AD, an administrative distance of a 1. Now, I say by default, we can play some games with the floating static route. That's a topic for another course. But yeah, OSPF is a 110. So it's more believable than RIP at 120. It's more believable than ISIS at 115. It's less believable than EIGRP at 90, by the way. But some more terminology before we get into some of how the stuff works. The way these two routers are going to start forming a relationship, it's like when you meet somebody. What's one of the first things you say when you want to establish a relationship with somebody? You might say, hello. And that would initiate the conversation. That's what these routers do. They say hello to one another. And they're going to exchange information, if they're adjacencies, using information, those puzzle pieces that we were talking about. LSAs contain information about how everything is interconnected. But here's a common misconception. Please make a note of this. I might say it incorrectly as well, because this is the way a lot of people think of it. When a router is sending that information to a neighboring router, an adjacency, it's not sending an LSA quote-unquote packet, it's sending an LSU packet, a link state update. That's the type of packet that carries an LSA. So the vehicle is the LSU, the link state update, but the passenger, the actual information, that's the LSA. And after we've done a bunch of exchanges and we're trying to build our database, usually routers are going to have information that's missing. I'm missing this piece to the puzzle, like the holly leaf on my snowman that I was talking about. Well, I can ask, hey, does anybody have that holly leaf? We can ask for missing information from our neighbors, and that's called a link state request. And if somebody has it, they're going to give it to us inside of a link state acknowledgement. So at this point, just to kind of sum up what we've talked about so far, we said we're going to have a bunch of routers. Those routers are going to build a map of the network. They're going to exchange LSAs to do that. And then they're going to run the Dijkstra algorithm to figure out the best way to get from point A to point B in that network. And I said that two routers that exchange information were called adjacencies. And I said there's also a neighborship. This is another common point of confusion among students. So let's contrast a neighbor with an adjacency. And as a metaphor, I'm thinking where I live right now, my wife and I, we built this home back in 2019. We've been here a little over 2 years now. And it's kind of isolated, honestly. On this road, there are only two neighbors really anywhere near us. I've got a neighbor just down the road from me, and there's a neighbor just down the road from them. Now, the one that lives right next to me, we have a much closer relationship than the other neighbor. I mean, we've been to each other's homes. We've collaborated on different little projects around the yard. We've texted, and we help each other out. We have more of a tight relationship. We exchange information. The other neighbor, kind of embarrassed to say it, but I'm not sure I would recognize them in public. I see them go by. I'm pulling out of my gate, and I see them go by in their vehicle. I say hello. I wave at them, but that's it. I just say hello. We don't exchange information. That's what an OSPF neighbor is. They exchange information, or they just say hello. They don't exchange link state advertisements. So a neighborship is when two neighbors, they exchange hello messages. They know about the existence of one another, but they're not very acquainted with one another. They're just saying hello. And the way they say hello is through multicasting. With multicasting, we're going to be using the multicast address, if you want to put this in your notes, of 224.0.0.5. That way, not everybody on this subnet has to see these hello messages, that they're only going to other OSPF speaking routers. But let's take it a step further. What is an adjacency where we do have a closer relationship? Well, to be an adjacency, first requirement is you've got to be a neighbor. I mean, the neighbor that lives next to me that I said we have a closer relationship, they are my neighbor. We do say hello, but it goes beyond that. But as a prerequisite, we first got to be neighbors. But then I said we exchange information. That's what these adjacent routers do. They exchange link state updates that contain that information. They exchange database description packets, which talks about the structure of a database. When later on in our session today, we'll go through the steps of setting up an adjacency. There's a lot of different states that OSPF can be in, and we'll learn more about the database description packets there. But to be a neighbor, this is important to know. For the ENCOR exam specifically, this is important to know. In order for one router to become a neighbor with another router, they got to be in the same area. Now, an area, we'll talk a lot more about areas later, but to be in an area is a grouping of OSPF routers. It could be the entire network. We could have all the routers belong to the same area. That might be fine. It depends, but it might be fine. But if I've got my network divided up into different areas, so I've got two different databases, in order for a router to become adjacent with another router, they got to belong to the same area. And we're going to see authentication. That's our last topic today, in fact. Authentication is got to match. I mean, if one side has a password that doesn't match the other side, yeah, we're not going to be setting up that relationship. And we got to be on the same subnet. We got to be on the same, because there's one link interconnecting us. That one link is probably going to be a single subnet, on a single subnet. So that's got to match. Timers that we'll talk about a little bit later, those have to match. We'll also talk about, in just a few minutes, different types of areas. Check this out. This gets wild. This is what I said is so difficult for students to understand, but I promise I'm going to do my very best to simplify it for you. We have just regular areas. We have stub areas, totally stubby areas, not so stubby areas, and totally not so stubby areas. Yeah, we'll get into all that, but the stub flags have to match is the bottom line. I cannot have a router with an interface in a stub area form a neighborship with a router whose interface is not configured to be in a stub area. And the MTU has to match. The maximum transmission unit. If one side is set to 1,500 bytes and the other side is set to like 1,470 bytes, that's not going to work. Oh, I said I would give you some troubleshooting tips along the way, and we are targeting the exam, so you might want to jot this down. If we did have a couple of routers, that are connected, but they have mismatched MTUs, the result, if I said show IP OSPF neighbor, you know what I would see as the current state? It would be the xstart/exchange state. I'd like you to know that. That might be useful information to memorize and to definitely put in your notes. Oh, by the way, I mentioned that we had like 600 plus people joining us right now. It seems to be growing as I say that. But I see a bunch of questions coming in. We are going to have some Q&A breaks, so please don't get upset if I'm not pausing to take your questions. We'd never get through class like that, but I will have some dedicated Q&A breaks. So if you do have a burning question, you might just want to jot it down, and then when I open it up for Q&A, I'll try to find some really great, relevant questions. So I just didn't want you to be offended if I'm not ignoring you. I'm just waiting for our Q&A break to answer some questions. Now, here is one of the... I'm not mad, I'm just disappointed in OSPF, as a parent might say. OSPF's metric calculation was probably fine 10, 20 years ago, but the defaults, now by the way, some of the newer equipment that you might find in data centers, they've addressed this. It's better on some equipment, but your traditional Cisco iOS router, they got issues. And I'll explain that. But first, before I get into the issue, let's explain how OSPF does its metric calculation. Its metric calculation is in terms of cost. And we said that cost is a function of bandwidth. So if I've got a 100 meg link, what's the cost? Well, here's the formula. You might want to jot this down. Cost equals something called the reference bandwidth divided by the interface bandwidth. What is the reference bandwidth? Well, the reference bandwidth by default on most of our just traditional Cisco iOS routers, even with the newer versions of Cisco iOS, the reference bandwidth is 100 meg, 100 megabits per second. So if I've got a 100 meg link like I have between R1 and R2, the cost is 100 is my reference bandwidth divided by 100. That's my link speed. 100 divided by 100, that's 1. I got a cost of 1. Okay, let's go through this. I've got a 10 meg link down at the bottom. You see between R1 and R3, what would its cost be? Well, that's the reference bandwidth of 100 meg divided by the link speed of 10 meg. 100 divided by 10, that'd have a cost of 10. So let's see, I want to go from PC1 to PC2. So R1's trying to figure out what's the best way to get to PC2. I could go through R2 and then down to R3, or I could just go directly over to R3. Now, if I were using RIP, for those of you that remember the routing information protocol that uses hop count as its metric, here's what RIP would do. RIP would say, how many routers do I have to hop through in order to get to that destination network? So R1 would say, well, I could go through R2 and then I could go through R3 and then finally I get there, or I could just go through R3. That's a shorter path. And RIP would go from R1 to R3 and think it did a good job. It did not consider the bandwidth. It went over a much less efficient link. So let's do the calculations that OSPF will do. It'll say that bottom link, 100, the reference bandwidth divided by 10, that's a cost of 10. All the 100 meg links, well, that's 100 divided by 100, that's going to be a cost of 1. So if I went from R1 to R2, and then as I go out of R3, that adds another cost of 1, because that's a 100 meg link going down to PC2, that's a total cost of 3. What if I went from R1 directly over to R3? Well, it's a cost of 10 just to get to R3, and then it's another cost of 1 to get out of R3. That's a cost of 11. So clearly, from OSPF's perspective, and I would agree with this, the most efficient path is from R1 to R2 to R3, and then out to PC2. That's the way that OSPF, by default, does its cost calculations and its route selection. However, here's the issue. What if I had a gig link? You tell me, chat it in. What is the cost of a gig link by default with OSPF? Go ahead and chat it in. And I realize there's like a 10 to 15 second delay from the time I ask something to the time you hear it. So I'm currently in the midst of killing 15 seconds to give you time to type it in. Okay, we got a lot of people saying 1. Oh, it's just flooding in here. Yeah, lots and lots of people are saying 1. Yeah, because the cost cannot be a decimal value. So yeah, 100 meg divided by 1,000 meg, that's 0.1. We cannot have a decimal. It's got to be an integer, so we round up to a 1. So you mean a fast Ethernet link at 100 meg has the same cost as a gig link? What about a 10? Same thing with a 10 gig link. Its cost will be 0.01. Still has to round up to a 1. So my problem with OSPF by default is that it is not distinguishing between a fast Ethernet link and a gig link and a 10 gig link. I think that's horrible. And there's so many administrators out there today that don't either think about it or they don't regularly do it. And there's a lot of networks out there that might be suboptimal. So how do we fix that? We need to get a reference bandwidth that's bigger. Now, my personal preference is to pick something that's going to give me a lot of future proofing. I like to set, sometimes I set 2 terabits per second, but lately I've just been doing 100 gigabits per second because that will give me different cost values for link speeds all the way up to 100 gig. And yes, I know there are some 400 gig transceivers out there, but I don't have any of those. So I'm typically setting mine at about 100 gig. So, and I'll show you how to do that in the live interface in just a few moments. But let's think about a bunch of routers all connected into a switch. They all belong to the same subnet. And if they're going to exchange information with one another, I said for one router to exchange information with another router, what was the requirement? Could it be just a neighbor? No, it had to go beyond just being a neighbor. It had to be an adjacency. So let's say that I've got these 6 routers on screen, and I want each router to be able to talk and send its information to every other router so everybody can agree on what this topology looks like. In order to do that, we've got to have a full mesh topology. Every router has to talk to every other router. And the problem is this just does not scale well. Now, this is not even that many routers. This is only 6 routers. Here's the formula, by the way. If you want to figure out the number of adjacencies that have to be formed, we say n times n minus 1, where n is the number of nodes. So here the number of nodes is 6. We got 6 routers. 6 times n minus 1, 6 times 5, and then divide that by 2. So that's 30 divided by 15. It'd take 15 adjacencies. Not horrible. What if I had 10 routers? That's 10 times 9 divided by 2. That's 45. You see how this just doesn't scale on what's called a broadcast network? Remember, if we're all connected to the same subnet, we're saying that we're all connected to the same broadcast domain. And in a broadcast domain, one router needs to get its information sent to all the other routers. This is not a good way to do it. This is where something called a designated router comes in. What we can do is elect a router as the DR, the designated router. By the way, if it goes down, we're going to have another router as a backup. It's called the BDR, the backup designated router. But they're going to be sort of a relay station for all this information. If all of my other routers can form adjacencies with just the DR and the BDR, that's going to dramatically reduce the number of adjacencies that we have to have. R3 only has to be an adjacency with R1 and R2, my DRs. It no longer has to be adjacent with R4, R5, R6. This is huge savings. And when R3 sends its information up to R1, R1 will replicate that out to everybody else in the area because it's got adjacencies with everybody else in the area. So for broadcast networks, or multi-access networks, where we've got a bunch of routers sharing the same subnet, yeah, this is massively helpful. Here's a question though. If I'm wanting to send adjacency information out there, I just want to talk to my DR. I said earlier, if I'm sending a hello, I'm sending that to 224.0.0.5. What if I don't want to talk to everybody? I just want to talk to my DRs. Well, there's another multicast address for that. And you might want to jot it down. I've got it for you on screen. Or stay to the end, and I've got those downloads for you, for anybody that's live and stays with us till the end. But we're going to go to 224.0.0.6. That's how we talk to just the DR or the BDR. And the next logical question is, all right, who becomes the DR and the BDR? Well, there is an election that's held. We're going to vote on who is the DR and the BDR. And it's by default, it's whoever has the highest router priority. Now, by default, you just set up OSPF on a router. The default priority, well, you tell me. Who knows what the default priority is for OSPF? Who can be the first one to chat that in? Go ahead and chat that in. I'm looking at all the different interfaces here. And I'm seeing it first on, again, I'm killing that 15 seconds. Who can tell me the default priority? It's not 100. Yeah. Wow. I'm not able to, no pass something. I'm not able to pronounce that. But yeah, it's 1. It's 1 by default. So if you just took everybody together, it's going to be a tie. So I'm a big fan of setting the router priority. So it's your decision who becomes the DR and the BDR. You might want to put that responsibility on some of the more powerful routers. Here's how you set the priority. You can go into you go into interface configuration mode for that subnet that everybody belongs to, and you say IP OSPF priority, and you give a number. Higher is better. So you might set your DR as a 10. You might set your BDR, the second best, at a 5. And everybody else can stay at a 1. Or if I've got this router that's really, really busy doing other stuff, and I don't want it to be a DR, it's too busy for that. we can say, I refuse to be elected. I will not run, and if elected, I will not serve. We can say I'm out of the election by saying that our priority is 0. Set the priority to 0, and suddenly we're not going to be considered for that election. But if we just leave everything at a tie, what happens then? Here's the tiebreaker. Routers in OSPF are going to be known by their router ID. And I like to go in and set, like on R1, I might set a router ID of 1.1.1.1, so that kind of gives me an intuitive notion that that's R1. And R2, I would say your router ID is 2.2.2.2. Now, yes, those do sound like IP addresses, and they are, but I'm not saying that I'm going to get you to 1.1.1.1 or I'm going to get you to 2.2.2.2. It's just a name. The router ID is just a name. Yes, it looks like an IP address, but we're not advertising that. So many people miss that. But I can go in and set the router ID. Here's how I do it. In router configuration mode, it's router-ID, give the ID, like 1.1.1.1. What if we don't do that? What's the next tiebreaker? Well, the next tiebreaker is, all right, let's look to the loopback interfaces on these routers, and whichever loopback interface has the highest IP address, that IP address is going to be the router ID. What if we don't have loopback interfaces? All right, final tiebreaker. If we don't have loopback interfaces, we're going to look at all of our interfaces on the router that are up and that have IP addresses, and whichever interface has the highest IP address, that's going to be our router ID. What if we haven't gotten around to setting IP addresses on the interfaces yet? You cannot configure OSPF. Try it sometime. Try to set up OSPF before you assign IP addresses. You won't be able to. It won't let you. Now, let's get back to that concept of areas that I talked about. I said that we could take a topology and chunk it down into different areas. And each of these areas would have their own map. It would be a map just of their area. It wouldn't be a map of everything. And when we ran the Dijkstra algorithm, we would just be doing it on our area. Like here, I've got these 9 different routers, and I've divided them up into 3 areas. Area 0, that's called my backbone area. And notice that there are a couple of routers that sort of sit on the boundary, on the border of these more than one area. Those are called, for your notes, those are called ABRs, area border routers. And an area border router is going to, we'll talk about this when we get into LSAs, but it's going to let one area know what networks are available in this other area. We're not going to run the Dijkstra algorithm on that other area. It's just going to say, here, it does, for example, R3 does not say to the routers in area 1, it doesn't say, hey, you want to get to area 0? Here's a map. No, no, no. That's the whole point. We don't want to run the Dijkstra algorithm on the area 0 map if we're in area 1. It just says, here's a listing of networks available in area 0. And the initial reason that Cisco used to give in their design guidelines for breaking a network up into different areas was, we don't want to overwhelm the router processor by running a Dijkstra algorithm on too big of a database. In fact, it reminds me, years and years ago, maybe 15 years ago, I remember my wife had an SUV, and it had one of the early versions of navigation systems in it. And I remember one time we were going to go on vacation, and we're in Kentucky, and we were going to, I don't know, Florida or somewhere. And I was like, okay, what's the shortest path? Well, it said, well, we just got this one little region of the United States loaded in this map. You're going to have to add on this other map. So it didn't want to run the Dijkstra algorithm on the entire map of the United States. It made us load in these different areas of the country, like, where do you want to go? All right, got to load that area in. But while that was a good intent early on, it stuck around too long, in my opinion. Here's what I mean. When Cisco used to have a design recommendation that said, if your area grows beyond 50 routers, you need to break it up into more than one area, because that's getting too big for the Dijkstra algorithm to run without burdening your router's processor. You know what that limit, or what they base that on? They base that on the Cisco 2500 series router. Anybody still have a 2500 series router? Those are old. I mean, those are very old. Those are like mid-1990s routers. And I actually have one though. I use mine for to access the consoles of some of my other devices. So I use it as what's called a terminal server, but I wouldn't want to route with it because it is slow. Today's processors in our new routers like the ISR second generation, third generation, they are literally orders of magnitude more powerful than those old 2500 series router processors. The bottom line is this is no longer a concern. I'm no longer, when I worked at Disney, I said we had over 500 routers. If we were running EIGRP, by the way, but if we were running OSPF, I wouldn't have any hesitation about making them all the member of the same area because modern routers can handle that. Now, there may be a time when I would want to break my network up into different areas. Let me give a couple of examples. One would be data centers. Not because if you go into a lot of data centers, there are tons, I mean tons of different subnets in there. In fact, we run out of VLAN names, so we have to go into something called VXLANs. That's a topic that you get into in the ENCOR course. But we can run out of 4,000 plus VLANs. There's a lot. I might want to put that in its own area, not so I'm saving the router processor, but it's because I'm saving myself. If I'm looking at a link state database, I don't want to see all those other gazillion routes that's in my data center. So just for my own sanity, I might break the data center out into its own area. Maybe another reason, one person is saying that maybe a couple of companies merge. That might be a reason to have different areas. I totally agree with that. In fact, it's kind of blending in with what I was about to say. If I'm about to attach something to my network that's not proven itself yet, maybe like that other company's network, or maybe I buy vendor X's piece of equipment, and I'm really not sure how well it does OSPF, I don't want it corrupting my database, so I might put it in its own area just as a safety precaution. But OSPF areas, if you have more than one, you've got to have what's called a backbone area. And that area has to be numbered 0. Or your area numbers can be in the form of dotted decimal. They can look like an IP address. They could be in the form of something like 0.0.0.0. That also counts, by the way, as a backbone area. But every other area must touch the backbone area. And if it doesn't, we'll talk about a workaround a little bit later on today. But now, let's get into one of the most challenging topics in OSPF, link state advertisement types and different area types. I'm going to take this nice and slow, try to tell some stories along with it, so be ready to take some notes because out of everything today, from the students I've had for over 2 decades now, this is one of the most challenging pieces of OSPF to understand. But let's take it nice and slow. Again, an LSA is just a piece of information. It's a puzzle piece. But there are different types of puzzle pieces, different types of information. And here, super simple topology. I've got 2 areas, and I've got router R1, R2, and R3. Now, R1 to R2, we'll say that's an Ethernet link. R2 to R3, that's going to be a point-to-point link. And we'll see later today when we get into different network types. Point-to-point links, they only have 2 routers, one at each end. There's no need for a DR, so they don't elect a DR. It's important to understand that. And the first LSA type is called a router LSA. A router LSA is going to be generated by a router for every network to which it attaches. So if I'm R1 and I'm attached to I've got 5 interfaces attaching to different networks, I'm going to be sending out within my area 5 type 1 LSAs because that's who I am attached with. There is another type of LSA that gets flooded within an area called a type 2 LSA. This is also telling us about links within that area. For your notes now, in order for a router to generate a type 2 LSA about a link, that link has to match 2 criteria. First criterion is that link has to be again, please write this down, it has to be a transit area. In other words, it has to be going from one OSPF speaking router to another OSPF speaking router. It cannot be going from an OSPF speaking router out to a switch connected to a bunch of PCs. In other words, it has to have a neighbor going that way. We got to go from one router to another router. That's a transit area. If we're not transiting between two routers, then that network link, we will not be generating a type 2 LSA for that. So within an area, we've got these two types. Type 1, a router is going to advertise that for every connected interface, and we'll have the same number of type 2 LSAs as we do links in that area that, number 1, are transit areas. Oh, and number 2, I didn't mention this. Number 2, it has to be a link on which you would elect a DR, a designated router. That's the second criterion. Now, on that link between R1 and R2 on screen, you think we're going to elect a designated router? Yeah, even though there's only two routers, I said that was an Ethernet link. That's considered to be a broadcast type of network. So yeah, that would be considered, or we would elect a DR there. But I said the link between R2 and R3, that's a point-to-point link. As we'll see later, they don't elect a DR. So notice on screen, I show a type 2 LSA for area 0. I'm not showing a type 2 LSA for area 1 because there's no DR elected on that link. Now, here's where things get interesting. How do we let area 1, or rather, how do I let area 1 routers know about networks available in area 0? We do that with a type 3 LSA. And I'll tell you right now, I do not like the name of a type 3 LSA. It's called a summary LSA. The reason I don't like that name is when I hear summary, I think of doing like network summarization, where we're taking a bunch of routers with a bunch of bits in common and we're doing a single advertisement, which we will do today, by the way. But that's not what this is. We're not doing network summarization, so I really dislike that name of summary LSA. Great news, we'll see this later. OSPF version 3 changed the name to something much more explanative. Is that a word? But explains it a lot better. But a summary LSA is going to give summarized information. That's the best way I want you to think of it. A summary LSA going from area 0 into area 1 is not saying, hey, I want you to be able to get to all these networks in area 0. I'm not going to give you a map of area 0 because that would defeat the whole purpose of breaking these things up into different areas. I'm going to give you a listing of networks that are available here. I'll say you can get to this network, or this network, or this network, or this network, but I don't give you any other information. I don't say how they're interconnected. I don't give you cost information. I just say, hey, if you want to get to any of these networks, come to me. Me being, in this case, R2. That's the ABR, the area border router. We mentioned this earlier, but make sure you understand, and it's in your notes, an area border router has at least one interface in more than one area. So when, and by the way, R2 now, it's got two link state databases. It's got a database or a map for area 1, and it's got a map for area 0. And it's going to take the networks available in area 0, not the map, but the networks available, the list of networks available in area 0, and it's going to say, all right, area, and here's another misconception. All right, area 1, here's a type 3 LSA for 10.1.1.1 or 10.1.1.0/24. Here's another LSA, type 3, for 10.2.2.0/24. The point is, it generates a type 3 LSA. Hear me on this. This is super, super important. You'll see later. It generates a type 3 LSA for every single network in area 0. If I had 12 networks in area 0, I would send 10, or what did I say, 12? I'd send 12 advertisements, 12 type 3 LSAs into area 1. Keep that in mind. We'll revisit that. And that's basic OSPF only networks. However, if we start to look at this, we might realize that this doesn't seem super efficient, does it? I mean, take a look at area 1. Does it go anywhere else? No, it's just sort of off on the edge of the network. If it's going to go anywhere not within area 1, it's going to go through R2 to get there. So instead of R2 sending me let's say, a dozen type 3 LSAs for the dozen networks in area 0, what if instead it sent me it just sent me a summary LSA, just one LSA? Hold on to that thought. We'll come back to that because we can do that. I can say, here's just a summary LSA, but keep that in mind. I'm going to revisit that in just a second. But let's say that R1, a couple of companies merge. R1 now not only connects to an OSPF network off one interface, it now connects to this other company that we just merged with. It connects to its EIGRP network. Here's another term for you. R1 has now become an ASBR, an Autonomous System Boundary Router. It's sitting at the boundary of two autonomous systems, the EIGRP autonomous system and the OSPF autonomous system. And R1 is going to have to be configured for redistribution. It's going to redistribute those EIGRP learned routes into OSPF. And let's say that EIGRP is advertising 50 routes into OSPF. So when those routes come in from R1, those are going to come in as a type 5 LSA. So in your notes, that's an AS external LSA. So a network coming from another autonomous system, like EIGRP, like RIP, every one of those networks are going to be advertised with their own unique type 5 LSA. So all these type 5 LSAs, they flood into area 0. And they get added to the database. How do we get that over to area 1 though? Do we just send those in a series of type 3 LSAs? No, those aren't type 3 LSAs. Those are type 5 LSAs. So R2 is going to say, wow, I just got this flood of networks coming in from this other autonomous system. I guess I better tell area 1 about that. So what it's going to do is send all those type 5 LSAs into area 1. But the routers in area 1, they got a problem. Everybody in area 0, they know about the autonomous system boundary router. They know that R1, yeah, that's the way that we get out of our autonomous system. That's our ASBR. Area 1 routers don't know that. So we have to give area 1 routers an additional piece of information. We have to say, oh, by the way, if you want to get to any of those networks advertised by a type 5 LSA, I guess I better tell you the ASBR so you know where to send it. So we send a type 4 LSA. That contains the address of the ASBR. That's how we get out to that other autonomous system. Now, let's try to make this a bit more efficient. I was hinting at this earlier. Now we can do it. Let's think about the fact that area 1 is receiving all these type 5 LSAs coming in from EIGRP. And the only way for us to get back to those networks advertised by type 5 LSAs, we got to go through R2 to do it. Or we're going to have to go to R1. R2 is our path to get there. It's like a default gateway to get back to all those networks. So instead of advertising like a dozen type 5 LSAs into area 1 and making its database bigger, wouldn't it be more efficient to just send what's called a type 3 default LSA? A default LSA says, hey, if you don't have a specific route in your database for what you're trying to reach, go to R2. That's your default. That's who you're going to go to with your default LSA. So all those type 5 LSAs, we no longer have to send those into area 1 because we just send a default LSA that says, if you don't know something more specific, go to R2, go to your area border router. And we give a special name to an area like that, to area 1 in this case, where we are summarizing those routes coming in from another autonomous system. It's called a stub area because it's sort of just sticking out on the edge of our network. It's not connecting to any other autonomous system. It's just on the edge. It's a stub area. We talked about the different stub flags earlier. It's a stub area. Let's take that logic one step further. We just said that the only way I can get to those type 5 LSA networks is to go to R2. So don't send me 20 or a dozen type 5 LSA advertisements. By the same logic, If I had 5 networks in area 0, do I really need to have 5 type 3 LSAs flooded into area 1? I mean, if it's not in my area, I'm going to R2. No matter if it's in area 0, no matter if it's in area 0P, there's only one way to get out of my area. And I've already got a database for my area. So what if we use this logic and said, if it's not in my database, then I just need to go to R2? I think that's valid. So instead of sending individual type 3 LSAs for the area 1, or excuse me, the area 0 networks, what if I just said, let's just send a single type 3 default LSA? This is going to say, it's like a default route. If the network you're trying to reach is not in your own link state database, go to R2. That's what R2 is saying with its default LSA. That's going to make the database much more efficient for area 1. And the name that we give to that area is a totally stubby area. A totally stubby area. Let's take it a step further. Let's say that R3 suddenly connects to another autonomous system. We're doing a lot of merger and acquisition in this business. We just bought another business and we're connecting them into R3, and they are running RIP. They're running the Routing Information Protocol. Oh, by the way, for this discussion, let's assume that area 1 went back to just a stub area. So in other words, I'm still sending those individual type 3 LSAs from area 0. So we're back to a stub area, but then suddenly I connect a RIP network or RIP autonomous system to R3. Suddenly we're not so stubby. And that's the name of the area type. We're a not so stubby network. We're kind of stubby. We're getting this. We're getting these default LSA, this default LSA for all those external routes in EIGRP, but I guess we're not totally stubby because I'm connected to another autonomous system. So here's the logic. I've got all these routes coming in from RIP. We got a problem here. Follow me on this. This is the brain twister. I've got all these. Let's say I got 10 networks that I want to advertise from RIP into area 1. And I send all these advertisements into R3. And R3 says, oh, external routes, what was it, a type 5 we used to advertise those? Oh, wait, there's a rule. And that rule says, thou shalt not send a type 5 LSA into a stub area, which is what we're saying R1 is right now. Huh. You mean I need to inject these routes from another autonomous system, but I'm not allowed to use a type 5 LSA? Here's what R3 says. It says, oh, I got an idea. I'll just call it something else. I'm not allowed to use type 5, so I'll say, oh, here's some type 7. Yeah, that's it. Here's some type 7 LSAs, wink, wink, as we send those into area 1. It's the same information that would be carried by type 5 LSAs. It's information from another autonomous system. But R3 says, I know it cannot use type 5, so I'll just call them type 7. And I send those into the area. R2 sees that, and R2 says, really? Really, R3? That's what you're trying to do? I know what you're doing. Those came from another autonomous system. I'm going to call them what they are, type 5 LSAs. So R2 is going to attack those type, quote-unquote, 7 LSAs, and it's going to say, I know they are really from another external system, so I'm going to send those as type 5 LSAs into area 0. Oh, by the way, for all those routers in area 0 that want to get back to those RIP networks, they got to know the ASBR. They got to know the autonomous system boundary router to get there, and that's R3. So we've got to send a type 4 LSA in there. But that's suddenly a not so stubby area. It was a stub area, but then we connected another autonomous system. So now it's not so stubby. One more type. I said that we were starting off with area 1 being a stub area, meaning that it was still receiving individual type 3 LSAs from area 0. And again, we said that's not super efficient. We don't need to do that. Why don't we just send a single default LSA into area 1? That'll get us to the EIGRP networks. That'll get us to the area 1 networks. So yeah, let's make area 1 that totally stubby area again. But we're still connected to RIP. So here is what we call it. Not even kidding. it's a totally not so stubby area, or it's typically written as a totally in SSA. That, my friends, is how type 1, 2, 3, 4, 5, and 7 LSAs work. Those are the main ones I would want you to know for certification. Just for completion's sake, I want you to know that there are some other ones out there. So let me give you just most of this, probably not super exam relevant, but I want to, for completion's sake, I want to cover it with you. There is a type 6 LSA that I predict none of us will ever use. About 20 years ago, Cisco had a multicast course that I taught. And in that course, I remember teaching a protocol that would route multicast groups or group addresses. And it was called multicast OSPF, MOSPF. What did it use to advertise those multicast networks? Type 6 LSAs. But I'm not sure I have ever seen in production a network using multicast OSPF. Instead, what is pretty much the industry standard is called PIM, Protocol Independent Multicast. So if you're running multicast, we're independent of the routing protocol. In other words, it could be OSPF, it could be EIGRP, it could be, perish the thought, it could be RIP version 1. It's independent of your unicast routing protocol. So I doubt that you'll ever see a type 6. Now, you will see a type 8. Those show up with OSPF version 3 all the time. There actually is a type 8 used with OSPF version 2, and it can carry BGP attributes for OSPF version 2, but you'll probably not see it in that context. You'll see it with OSPF version 3, and we'll look at that OSPF version 3 database later today, and I'll point out the type 8 LSA. That's where we're advertising information that's on a link. Maybe there are 3 routers. It's on the same subnet, in other words. We're advertising addresses, including link local addresses, on that link. On that subnet. There's a type 9. Now, it did have a use in OSPF version 2 that I don't think you'll ever see. It could carry some extra OSPF information if both ends knew how to interpret that. I've never seen that used. But you will see it with type OSPF version 3. Here, it's carrying information about the links within a network. And I know what you're thinking. You're thinking, wait a minute, didn't type 1 and type 2 LSAs carry all that information? They did, but interestingly, they didn't include the IP address information for those links. So type 9 does. Type 9 is like a new and improved compilation of type 1 and type 2. Now, type 10 LSAs, you're typically going to see these with multi-protocol label switching and service provider environments because they can advertise some information that can be used for traffic engineering. And there is a type 11, and it's just like a type 10. It's still used for primarily OSPF, or excuse me, it's used for multi-protocol label switching. The only difference is you don't send a type 11 LSA into a stub area. It's just kind of like you don't send a type 5 LSA into a stub area. Same thing with type 11. So again, just some extra information for completion's sake. Now, before we take our first Q&A break, I do want to do a configuration with you. So I'm going to take us out to some live gear, and we're going to do a basic configuration of OSPF version 2. So let me move us out there. And here's the topology that we're working on that you see on screen. And I just want to set this up such that every router can see every network here. So let's go into router R1, and I'll go into global configuration by saying configure terminal. And then I'm going to start the routing process. I'll say router OSPF, and I'll just give a, catch this, I'm giving a locally significant process ID. This is not an autonomous system number, folks. If I were doing EIGRP and I said router EIGRP1, that would be an autonomous system number that would have to match on my neighbor. That's not true with OSPF. It does not have to match on my neighbor. I typically do match just so I remember what my process ID is, but it doesn't have to match. Now, I need to advertise the networks that R1 knows about. I'm going to say network. Oh, you know what? Let me do one thing first. I want to show you one thing first. We're going to be using something called a wildcard mask. And this wildcard mask can be derived from a subnet mask. We're going to be using a wildcard mask in this command, and some people get a little bit thrown when we talk about wildcard mask. So here's what I mean. It's sort of the inverse of a subnet mask. Let's say that I had a subnet mask of 255.255.255.0. From that, how do I calculate the wildcard mask? Here's the simple math. You ready? Create an address with all 255s. All 255s. And from that, you subtract your subnet mask. That's going to give you your wildcard mask. So in this example, let's say that I want to convert 255.255.255.0, that's a /24 subnet mask. I want to convert that into a wildcard mask. So on an octet by octet basis, I can say 255 minus 255 is 0. The next octet is 0. The next octet is 0. Finally, fourth octet, 255 minus 0 is 255. Let me challenge you with one now. My challenge to you is this. Can you give me the wildcard mask for 255.255.255.252? It's a /30 subnet mask. Go ahead and chat that in if you would. Yeah, Casey is the first one in with that I saw with the correct answer. Casey's saying it's 0.0.0.3. Excellent. I think you got it. Well, let's go back to our demo now that we understand wildcard masks. And let's say that I want to advertise that network off of R1's gig 0/1 interface, which is 10.1.1.0/24. Now, please hear me on this. This is another super common point of confusion. Here's the command that we'll give to advertise that network. This is the way we normally do it. We're saying, I want to advertise 10.1.1.0 and the /24. I'm going to put that not as a subnet mask. I'm going to put it as a wildcard mask, which we just said is 0.0.0.255. And I need to say what area that interface, not the router, but what area does that interface belong to? It belongs to area 0. Now, that command looks like I said, advertise network 10.1.1.0/24 in area 0. And that is the effect. That's what it does. But that's not exactly what the command is saying. That command is saying, here is a network address space. If you have an interface on this router whose IP address falls within that address space and it's currently up, advertise that interface's network. I'll prove that a little bit later on, but I just want you to understand that this command is not really saying advertise this network. I'm just saying here's an address space, and any interface whose IP address falls within that address space, advertise that, and it's up, advertise that interface's network. Again, I'll prove that to you a little bit later, but I'll just keep going as we traditionally do for now. And for the loopback interface, which is 1.1.1.1/32, I'll say advertise 1.1.1.1, and my wildcard mask is going to be 0.0.0.0, and it's also going to be in area 0. One interface to go, I'll say network, and this is the one going off of gig 2, or 0/2 over to R2. It's going to be network 172.16.1.0. Notice it's a /30 subnet. You see that on screen in the topology? That means I'm going to give a wildcard mask of 0.0.0.3. It's also in area 0. Now, I could stop here. Let me show you just a couple of extra things, and I didn't even include this in that script that I talked about giving you later on. Excuse me, I want to jot this down. But if you notice, there's one interface, gig 0/2 on R1. It's not connecting out to another router. Is there really any reason to be sending hellos out of that interface? In fact, that could be a security risk, couldn't it? Some malicious user could plug into switch 1 and they could configure a router plugged into switch 1 as an OSPF router, form an adjacency, and start corrupting our database. So if I don't want to send hellos out to that stub part of the network, I can say, I still want that network to participate. I still want to advertise 10.1.1.0/24. I just don't want to send hellos to it. I could make it what's called a passive interface. I could say, let's make gigabit 0/1 a passive interface. One other thing that we might want to do, because we talked about setting that reference bandwidth, yeah, let's make that a little bit more reasonable than 100 meg. Let's do this. I'll say, here's the command if you want to jot it down. Auto cost reference bandwidth, and I'm going to say 100,000. 100, the unit of measure is megabits per second, so 100,000 meg, that's 100 gig. And it's warning me, make sure you do this on all the routers. And I will, as we get this configured. I think I'm done on router R1 right now. Let's go to router R2. And I'll do this one quicker because it's basically the same. I'll say router OSPF locally significant process ID of 1. Network between R1 and R2 is 172.16.1.0. 0.0.0.3 is my wildcard mask. It's a member of area 0. Now let's be careful with the next one. The next one is my loopback interface, and it's not a member of area 0. Not a member of area 0. I'm going to say network 2.2.2.2 wildcard mask 0.0.0.0. It's in area 1. Got to be very careful to make sure you get the right areas specified. All right, we got one network to go, and that's between R2 and R3. I'll say network 172. Actually, no, it's not 172. It's 192, isn't it? 192.168.1.0. It's a /30 subnet mask, so my wildcard mask will be 0.0.0.3. It's going to be in area 1. Can I set up a passive interface on R2? I don't really see a big need to do that. I don't see a big need to do that. So, I do want to set the reference bandwidth, though. I'll say auto cost reference bandwidth 100,000 meg. All right, one router to go. Router R3, basically the same kind of configuration here. On R3, we'll say router OSPF. Again, I don't have to make these process IDs match. I just do so I can remember what they are. If I make them all the same, I'll remember. Now, let me prove to you what I said earlier. Earlier, I gave a network statement, and I gave one of the networks attached to the router, and it advertised that network. But I said the network command was really saying, here is a network address space. And if we have an interface that's up, whose IP address falls within that address space, advertise that interface's network and its subnet mask in OSPF. So what if I did this? What if I gave just one network statement? What if I give a network statement that encompassed all possible IP addresses? I'll say network 0.0.0.0 with a wildcard mask of all 255s. That encompasses every single IP version 4 address there is. And it's in area 1. That address space, by definition, encompasses the IP addresses of gig 0/1, loopback 0, gig 0/2. So that one command makes them all participate. Let's set the reference bandwidth. I'll say auto cost reference bandwidth 100,000. Make sure I got the right number of zeros there. 100,000. And, I've got another opportunity for a passive interface. I'm not connecting to a router out of gig 0/2 on R3. I'll say gig 0/2. All right. Let's see how we're doing now. Let's see if I have learned any of these routes. I'm going to say show IP route. And I have learned some routes on R3. Check this out. It says I learned 1.1.1.1. That's R1's loopback interface. I learned it via OSPF. That's what this O means. And this IA, that means it was from another area. It was an inter-area learned OSPF route. Because I'm in area 1, I learned it from area 0. So it's an inter-area route. Interesting. Now, I'll learn 2.2.2.2, but there's no IA. That's R2's loopback interface because it is in my area. Nice. Can I reach all the way across the network? Can I reach over to R1? Can I say ping 10.1.1.1. That's the gig 0/1 interface on R1. Yeah, that was successful. That's great news. Here's another great troubleshooting command you might want to jot down. Show IP protocols gives me a lot of detailed information about how my routing protocols are configured. It says that here's my router ID. I didn't set the router ID, so it went with my loopback interfaces we talked about. And it says I'm routing for everybody that falls within this address space, which is everybody. And here is my passive interface. Let me go to R2 because we've got a couple of neighbors there. On R2, I'll say show IP OSPF neighbors, and I see that I've got a neighbor with R1 and a neighbor with R3. Won't you be my neighbor? And we're in a full state, which is what we want. Excellent, excellent. Now, we said that OSPF is going to be building a link state database. Let's take a look at that. I'm going to say show IP OSPF database on R3. And we said we should have a type 1 LSA for every network link within an area. And I've got 2 links within my area. R1, by the way, loopbacks don't count. It's got a /32 mask. But I've got a link between R2 and R3 going off to SW2. And you see I've got two type 1 LSA, 2 router LSAs. I said I would have I would have a type 2 LSA for every link that was a transit link. It was interconnecting 2 routers and a link on which a DR would be elected. Well, these are all Ethernet, so DRs will be elected, but only one is a transit link. R2 to R3, it's going between 2 routers. R3 going out to switch 2, that's not a transit link. It's not going to another router, so I've only got one type 2 LSA. And we said, unless we start configuring stub areas and that kind of thing, we're going to see a type 3 LSA for every network coming from this other area. So these summary LSAs, I don't like that name, by the way, as we described. I've got these 3 networks, and it tells me the actual networks that I learned from Area 0. If you want to see the networks known to just OSPF and not necessarily the router's routing protocol or IP routing table, I can say show IP OSPF RIB. That's the routing information base. And this shows me the routes that OSPF knows about. And if it's got more than one route, it's going to indicate the best one with a greater than sign. And one other command that'll tie into some stuff we're going to do later today, show IP OSPF interface gig 0/1. It's going to give me a lot of information about that interface. It's going to tell me the cost of that interface. Because I adjusted that reference bandwidth, suddenly instead of having a cost of 1, I've got a cost of 100. Nice. It's a broadcast network type. We see the router ID. Lots of other great information in here. More on some of this a little bit later. All right, let's get into the second part of our session today, which is going to be on network types. Now, if you read the exam blueprint for CCNA and for ENCOR, they tell you that you need to know network types. If I remember correctly, CCNA says you need to know about the broadcast network type and the point-to-point network type. ENCOR adds on the non-broadcast multi-access and the point-to-multipoint. We're going to talk about all those today and some of their characteristics. The first is a broadcast network type. This is, think Ethernet. If we have an Ethernet switch and we have a lot of devices connecting into that Ethernet switch, if I send out a broadcast, it's going to go to all those devices. That's why we say it's a broadcast network. And because we have multiple devices connecting into a single subnet, that's why we say it's a multi-access network. We have multiple devices that can access that network. And I want you to understand some characteristics. You might, well, I started to say you're going to take notes, but you could take notes if you're not sticking around to the end, or if you're watching this on replay, but those that are with us live, you're going to be able to download this at the end. But yeah, if you're watching this on replay, absolutely take notes. But this is going to be the default OSPF network type on an Ethernet interface. We are going to be electing a DR and a BDR. And how often are we going to be sending hello messages out? 10 seconds. Every 10 seconds we'll be sending a hello message out. Compare that to point-to-point, which is just 2 routers, one connection between them. Maybe it's a serial link. some sort of a WAN connection, it's going to act differently. Do we really think about it? Do you think we need a designated router if there's only 2 routers on the link? I don't think so. I mean, the designated routers, that was trying to overcome the issue of having a full mesh of adjacencies. We're only going to have one adjacency here. And this is what we have by default on a serial interface on the Cisco router. Well, serial interfaces that are not configured for frame relay, to be specific. Also, I want you to know, well, we just said this, DRs and BDRs not going to be elected. The timer is interestingly the same as with broadcast. The hello interval is 10 seconds. Let's take a look at non-broadcast multi-access network types. This one is a bit confusing to folks. Let me break it down for you. This is a multi-access network. What that means is all these routers, R1, R2, R3, R4, they're all connecting in to the same subnet. They're all accessing, we got multiple devices accessing the same subnet. However, we're not doing broadcasts over these links. And by the way, when I say we're not doing broadcasts, that also implies we're not doing multicasts either. So we're not doing broadcast or multicasts. Now, that brings up the question, if I cannot do a multicast, how do I send a hello up to R2? Because I don't know where R2 is. I don't know. I send out a multicast. How do I know how to get to it? Well, with NBMA networks, we actually have to configure the IP address of our neighbors because we're not going to just dynamically discover it through multicast because we're not allowed to send those. And this is going to be the default on a frame relay serial interface. And we are electing DRs and BDRs because we're on a multi-access network. That's the big point I want you to get from this. If we're on a multi-access network, we are going to be electing DRs and BDRs. We have to specify who our neighbor is because we're not going to automatically find them. And the timer starts to vary here. It's going to be 30 seconds. It's 3 times as long as what we've seen up till now. And the final type is a point to multipoint. Now this looks about like the other one, doesn't it? The other one, all of these routers belong to the same subnet. That's not the case here. R1 in this case is going to have 3 sub-interfaces like serial 0/1.1, 0/1.2, 0/1.3. And there's going to be a subnet on each of those permanent virtual circuits. There's one subnet from one sub-interface on R1 up to R2. Different subnet going to R3. Different subnet going to R4. So this is not a multicast or a multi-access network. Therefore, we don't need BDRs and DRs, do we? And what's happening here is we're really treating each of those dashed lines, each of those permanent virtual circuits, we're treating each of those as point-to-point links. Separate point-to-point links. And on point-to-point links, we don't need DRs or BDRs. What R1 is doing is just replicating the information and sending it out the other links. And the hello interval is 30 seconds. Now, sometimes, I told you what we had by default. You can go in to an interface and say, here is your OSPF network type, by the way. And if you do that, it's going to change the timer information. And I want you to know for the ENCOR exam, which network types are compatible with one another. R1 has this type, R2 has this type. Can they form a neighborship? Let's go through some options. Obviously, broadcast to broadcast, that's what we have most of the time. So broadcast on R1, broadcast on R2, yeah, we're adjacent, or at least we're a neighbor. What about non-broadcast to non-broadcast? Sure, those match. Point to point to point, point to multi-point, sure, that matches as well. What about broadcast to non-broadcast? And by non-broadcast, I mean NBMA, non-broadcast multi-access. Actually, you can have a neighbor like that. The timers are different. Broadcast is 10-second hello. Non-broadcast or NBMA, that's 30-second hello timers. You can adjust the timers manually as long as you make the timers match. Yeah, you can have mismatched area types. Here's the key. Instead of just memorizing this big list, here's the key to memorizing this for the exam. If both ends support, or if both ends elect DRs, yeah, adjust the timers and you're good to go if you need to adjust the timers. If both ends don't elect DRs, yeah, they're going to be compatible as well. So, for example, point-to-point and point-to-multipoint, yeah, they have different timers, but they neither one elects a DR or a BDR, so you can be peers in that environment. Now, let's talk about timers. I keep saying there are all these different things that are a little... that can be a little bit confusing. This is one of them. This is timers. And the reason it might be confusing is if you work with EIGRP. EIGRP works quite differently than this, even though a lot of people think it's identical. Here's the way an OSPF timer works. We've already talked about the hello timer. And let's say that my timer is set to 10 seconds, like on an Ethernet port. So every 10 seconds, bam, bam, I'm multicasting out a hello message. And I'm receiving hello messages from neighbors or potential neighbors. If I don't hear from one of my, let's say I form a neighborship. If I don't hear from that neighbor within a certain amount of time, called the dead timer or the dead interval, I'm going to tear down that neighborship. I'm going to assume that they're no longer there. Something's happened to the link between me and them, so we just cut this off. So we have to hear a hello from our neighbor within the dead interval. And you'll notice that the dead timer is whatever the hello timer is, times 4. So if your hello timer is 10 seconds, your dead timer is 40 seconds. If your hello timer is 30 seconds, yeah, you guessed it, your dead timer, it's going to be 2 minutes, 120 seconds. And timers have to match to form a neighborship. We pointed that out earlier. Now, I said I would walk you through the different neighbor states. This is going to be one of those great reference slides for you. So if you're not attending this live, or you don't plan on sticking around to the end, you'll definitely want to take a screenshot of this after I have it fully populated. But these are the different neighbor states I would want you to know as we're trying to form a neighborship or possibly an adjacency. The first one is a router boots up and its OSPF neighbor state is down. Now what that means is I haven't received a hello from anybody. Now maybe I've sent a hello. Down doesn't mean I've never sent a hello. Down just means I've not heard any hellos from anybody else. Now, in the attempt state, please make a note of this one, you're only going to see this in an NBMA network, a non-broadcast multi-access network, where we have to specify the IP address of our neighbor. That's where we're sending hellos to that configured neighbor, but we've not received anything from that neighbor. It's about like down, except it's like the down state on an NBMA network. We can send hellos, we just haven't heard anything from our neighbor. So those are similar. Next is a NIT. Here, I did receive a hello from my neighbor. Yay, there's somebody out there that's talking to me, but as I look at their hello message, they're not giving me all the information. They're not including their router ID. Huh. What does that mean? If they sent me a hello message and they did not include their router ID, it means they've not heard a hello message from me yet. So maybe they were the aggressor. They sent the hello message first and I just haven't responded yet. That's what a NIT means. I mean, somebody's got to be first, so a NIT's not a bad thing. It's not uncommon. But finally, I've received a hello from my neighbor. It's got its router ID. They've received a hello from me. It's got my router ID. We are maybe at the final state. We're not sure yet. But we're in a two-way communication state right now. There's bidirectional communication. We are now neighbors. We're not adjacencies necessarily, but we are neighbors. And then we decide, are we going to form an adjacency? Well, that's going to depend, isn't it? Are we on a broadcast network, or I should say, are we on a multi-access network? And am I a DR, or am I talking to a DR or a BDR? That's where the XStart state comes in. This is where we're trying to elect a DR and a BDR for this multi-access network. That happens during the XStart state based on the priority. Now, during the exchange state, this is where we have elected a DR, or if we don't need a DR, we've skipped that step. But in the exchange state, we have adjacencies. So however many we have, whether it's one between a couple of point-to-point routers, whether it's a bunch of routers pointing to the DR and the BDR, adjacencies have been established. During the exchange state, we are sending what are called database descriptor packets, which is, I know it sounds silly, I don't mean to be trite by saying this, but database descriptor packets describe the database. That's about the only way I know how to say it. They're not populating the database. They're not saying this network is connected to this router and this is connected to this. No, it's describing like the nature of the structure of the database. Maybe the database is going to be this big. It's going to have this many entries in it. It's describing the structure of the database, but it's not populating the database. The population of the database happens during the loading state. This is where we're exchanging those LSAs. And if I'm missing a puzzle piece, if I need that holly leaf that we talked about earlier, I'm going to send out an LSR, a link state request, saying, hey, I'm missing a piece to my link state database. Can anybody give it to me? And my neighbor says, my adjacency says, yeah, I got that. And it sends it to me. So now everybody has built their database. They all match. We now have full adjacencies with everybody that we should have adjacencies with. And this is a steady state. But sometimes you'll be looking at your neighbor states. It might say two-way. That's totally fine. That just means that, yeah, this is a neighbor, but you don't have an adjacency with it. And I'm going to pause right there to let you take a screenshot. Because for those of you that are sticking to the end, I'm going to let you download today's slides. But if you're watching this on replay, or if you're not sticking around to the end, this is one to take a screenshot of. I'll give you a second to do that. All right, next up is route filtering. We've done the basics now. We said, here's how OSPF works in theory. We defined a bunch of terms. We did a basic OSPF version 2 configuration. We made sure everybody could see everybody else. We talked about how neighbors and adjacencies are formed, DRs and BDRs, and all the establishment states. Now let's start overlaying some fun features on top of the basics. The first one is route filtering, because we may not want every route to go in to our OSPF link state database. Maybe some of those routes coming from another autonomous system, I might not want those in my network. Maybe I've merged with another company and they're using the 10 dot private address space, and so am I. I don't want their 10 dot address space in my network, so I want to filter some of that stuff out. Now, here's the thing. With ENCOR, if you want to do route filtering, you can do that pretty much anywhere you want to. But with OSPF, you can only do route filtering at very specific locations. You can do route filtering at the ASBR, the Autonomous System Boundary Router. And it's done as part of your redistribution configuration. And that redistribution is not a topic for today. I've actually got a YouTube video on it if you want to go check it out. But that's covered as part of our redistribution configuration. So as you're going from one autonomous system into another, that's where you can set it up. Or as you're going from one area into another, that's another place that you can do filtering. Now, are you ready for me to bend your brain a little bit? What if I wanted to filter a network from one router within an area? Doesn't that seem to break the rules of what OSPF is all about? If I'm filtering from just one, I mean, think about this. Within an area, that's the rule. Everybody has to have identical maps. We all have to have identical link state databases. So how is that possible? Is that possible? It's not possible for routers in an area to have different link state databases, but remember, just because something is in the link state database, that's not a guarantee it's going to be put in the router's IP routing table. So we play this little trick. Let's say that we want to filter out 10.1.1.0/24. We can filter it as it goes between the OSPF database and the router's IP routing table. During that population of the IP's routing table, we just pick it out. We get rid of it in the middle before it gets to the router's IP routing table with something called a distribute list. I'm going to demonstrate that for you. And here's the topology we're going to use. I'll be doing filtering in two different ways in this demo. And we'll be setting this, and I'll be filtering on R2 as we go from one area to another. And I'll be filtering on R1 as we go from the link state database into the router's IP routing table. So let me get my topology back up on screen. We're using the same topology that we did before. And let's go over to router R1. And let's take a look at our routes. I'll say show IP route. And notice I know about a couple of loopback interfaces. One on R2, one on R3. Just for no particular reason, just because they're easy to identify. Let's say that we want to filter out those loopback interfaces. Well, where do I do that? We're going from one area to another area. That slide I just showed you said if we're filtering out routes from one area to another area, that's got to be done on where? It's got to be done on the ABR, the area border router. That's R2 in our case. So I'm going to go to R2 to set this up. And to configure this, I'm going to set up something called a prefix list. If you haven't worked with prefix list, I'll describe it as we go along. It's similar to an access control list because we have multiple entries as part of the same list. We have sequence numbers that determine the order of operation. We process it from the top down. So a lot of commonality with an access control list. But I'm going to say IP prefix list, and I'll give it a name. We're trying to get rid of loopback interfaces. Let's just say no hyphen loopbacks. And I'm going to give a sequence number of 10, which is going to be executed or evaluated before the sequence number of 20. Sequence number 10, let's deny the loopback IP address of 2.2.2.2/32. It had a 32-bit subnet mask. That's R2's loopback interface. Let's do the same thing for, I'll give it a different sequence number 20. Let's deny 3.3.3.3/32. What about everybody else? I said it had a lot of commonality with an access control list, which has what? At the bottom, an implicit deny everything. So does a prefix list. I don't want to block everything, so I've got to say, all right, permit everything else. So here's a final entry I'll make. I'll make it sequence 30. IP prefix hyphen list. No loopbacks, sequence number 30 this time. And I want to permit everybody that I've not already matched. And a way that I can specify all IP addresses is I can say 0.0.0.0, and I'll say a /0 mask, but check this out. I'm going to give a qualifier. I'm going to say the subnet mask can be less than or equal to 32 bits. Well, would you agree that every subnet mask is either less than or equal to 32 bits? I think so. That's a way that we can specify every possible IP version for address. Now, let's apply it. Let's go into router configuration mode for OSPF process ID 1. And I'll say area 0 because I'm going into area 0. Filter list, and I give the name. Actually, I say it's a prefix list. It's a kind of list. I'll say it's a prefix list. And it's named no hyphen loopbacks. And I'm going to apply it in the inbound direction as I go into area 0. And I think we're done. That's simple. So let's go back to R1 and see if it worked. Let's go to R1 and I'll do a show IP route. Do I still see those loopback interfaces? I do. Oh, I see mine, but I didn't block that one. But I no longer see 2.2.2.2 or 3.3.3.3. That's how we can filter routes going from one area to another area. Okay, let's take it to the next step. Let's filter one of the routes that router R1 knows about in its OSPF database, and let's filter that from showing up in the router's routing table. Let's filter, if you take a look at the topology, let's filter that route all the way over, hanging off of R3, going to SW2, 10.2.2.0/24. Let's find it here. Here it is, 10.2.2.0/24. It's an inter-area route. Let's filter that out of our routing table just on R1. And to do that, we cannot filter it out of the link state database. We just sort of grab it on its way from the link state database down to the IP routing table. And I'm going to use a prefix list to do that. I'm going to do it here on R1. I'll say IP prefix list filter underscore 10.2.2.0 is what I'll call it, because that's what I'm filtering. It doesn't have to say that. That's just the name. It's an intuitive name I gave it. We'll still give sequence numbers. The first sequence number I'll say is 10, and I want to deny that network 10.2.2.0/24. I want to permit everything else. So just like we did before, I'll say the last sequence number. I want to permit 0.0.0. Actually, yeah, let's try it. 0.0.0.0/0. And the subnet mask is less than or equal to 32, which is everybody. Let's go into our router configuration mode, and I'll say distribute list this time instead of filter list. I'll say, well, I just didn't give enough characters. Distribute list. It's a prefix list. And I want to make sure I type it correctly, so I'm just going to copy paste this. There's my prefix list, and I'm going to apply it in the inbound direction, meaning it's going into my IP routing table. Let's first make sure that 10.2.2.0 still lives and is alive and well in our OSPF database. I'll say show IP OSPF database. Yeah, there it is. It's still there. It came to us via a type 3 LSA, but is it in our routing table? 10.2.2.0, no, it's not. It is now conspicuously absent. So we've done a couple of things. We have filtered as we go from one area to another area, and we filtered as we go from a link state database within a router to that router's IP routing table. All right, next topic we got is route summarization. This is a way to have more efficient routing tables. Because let me give you an example. Let's say that I've got these four networks: 192.168.0.0.1.0.2.0.3.0. If we look at those subnets in binary, they've got a lot in common. If I break those octets down into binary, can you see that they all have the first octet in common? I mean, they're all 192. They've got the second octet in common. They're all 168. But if we look at that third octet and we break down 0 and 1 and 2 and 3, they have the first 6 bits in that third octet in common. So instead of advertising 4 separate networks and having 4 separate entries in my IP routing table, don't you think it'd be more efficient if I just had one advertisement that encompassed all 4 of those networks? I think so. So what if I did this? What if I said, well, we've got the first 22 bits in common, so what if I created a subnet mask that's 22 bits long? What would that look like in dotted decimal? Well, if you do the binary, that would look like 225.225.2 excuse me, I said 225. I meant 255.255.252.0. You remember how we get a network address? We set all the host bits to 0. So if I take all the 22 bits that are in common and I make the last 8 bits 0, this is what that looks like in binary. And if you convert that to decimal, we could advertise a network of 192.168.0.0/22. And that one advertisement would encompass all of those networks. That can be a big savings for us. Now, here's something to think about. If you have a summarized address or an address summary that you're advertising, you want to be very, very careful to make sure that there's not another network, another subnet somewhere in your network that also falls within that advertisement. That happens sometimes. I mean, in this case, I used all 4 addresses that advertisement was advertising. But what if I had in that third octet, what if I had a 0 and a 1 and a 3, but not a 2? I could have still used the same advertisement, but if somewhere else in the network I had that third octet as a 2, yeah, now the network, the router, it still should work, because if I have an entry for like 192.168.2.0, that's more specific. If it's a /24, that's more specific than 192.168.0.0/22, so it still should work. It's just, it can get you into trouble. So be careful with that. Now, just like we had specific places in which we were allowed to do route filtering, we've got specific places where we are allowed to do route summarization. And here they are. We can summarize at an ASBR as we're going from one autonomous system into another, or we can summarize as we're going from one area into another. I'm going to demonstrate both of those for you in just a second. If we summarize at the ABR, the area border router, we're going to use the area range command, and I'll show you that syntax. If we're summarizing at the ASBR, the autonomous system boundary router between like OSPF and something else, that's going to use the summary address command. Let me show you this. And here's the topology we're going to use. Notice I've got a bunch of loopbacks on R3, and they can all be summarized, just like we did before, with a /22 subnet mask. We're going to be advertising 172.18.0.0/22. That's going to summarize all the loopbacks on R3. On R2, we can summarize all the loopbacks with 172.17.0.0/22. So let's see how to do that. Let's go out to our live interface again. And I'm on, I need to move over to my other topology right now because I didn't have all those loopbacks on my previous topology. So I'm on a different set of 3 routers right now. And what we want to do is take a look at a couple of ways of summarizing these routes. One way is as routes are coming in from another autonomous system. Another way we said is when we're going between different OSPF areas. So let's say that I want to summarize those 172.18 networks. Those are R3's loopback interfaces. They're currently in EIGRP, and they're being redistributed into OSPF. And after we do that, then we'll summarize the 172.17 networks that are R2's loopback interfaces. And we'll summarize those as they're going into Area 0. So let's begin on R1. Let's just see what we have right now. I'll do a show IP route, and we should see all of those routes individually. Yeah, I've got all these 172.17 networks, and I've got all these 172.18 networks. All right, let's fix that. We can see from these 172.17 networks that they all have this IA code. That means they're coming from a different area. If you look at all the 172.18 networks, they have an E2 code. E2 means OSPF external type 2. That means we're coming in from another autonomous system. Not another area, but another autonomous system. Now, by the way, this is a redistribution topic, so I won't get into it today. We do get into it in ENARSI, by the way, and maybe even a little bit in ENCOR, but definitely in ENARSI. There's another one called a type 1, or rather an E1 external type. I'll just tell you right now that I'm a big fan of E1 as opposed to E2. I like to always change it to E1 because I think it gives a more accurate cost calculation, but I don't want to get on my soapbox about that, but yeah, we'll save that for the ENARSI class. But first, on R3, let's go over to R3, and let's summarize all those loopbacks living in EIGRP. We'll just do that one first. So I'll go into global configuration mode, router OSPF 1, and I'll say summary-address. Now this would not work between areas. The summary-address command is between autonomous systems. I'm going to give the summarized address of 172.18.0.0, and I'm going to give a 22-bit subnet mask, which is 255.255.252.0. That's it. We're donezo. What we're doing is saying we want to summarize networks that fall within that address space into just 172.18.0.0/22. Now, here's a question. A lot of people, or not a lot of people, but when you're doing like CCNA labbing and are trying to do some pretty creative things, you might say, well, I really want to be advertising that network, so I'm just going to say advertise that. That will not be advertised unless there is at least one subordinate route that falls within that address space. So if we didn't have anybody that really included, it would not be advertised. Did it work? I don't know. Let's go back to R1 and see. Let's do a show IP route. Do I still have all those 172.18 networks? Nope. I've got a summary. Look at that. 172.18.0.0/22. I no longer have to look at all those 4 individual networks. So we succeeded as we went from one autonomous system into another. What about within an area? Let's go over to R2 right now, and let's summarize all those 172.17 networks. Again, pretty simple configuration. I'll say router OSPF 1, area 1. And by the way, I'm saying area 1, and this sometimes is confusing. You might say, well, am I specifying the area that I'm going into or the area in which these addresses currently live? You're specifying the addresses, or you're specifying the area in which these currently live, which is area 1. So I'll say area 1 range 172.17.0.0 255.255.252.0. Oh, I should point something out here. If I give context-sensitive help, you don't have to do this, but you could specify an OSPF cost. I just pressed enter, so it did the default behavior. And I'd like to point out what that default behavior is. Let's say that I had, in fact, I did have 4 different networks that I'm trying to summarize. It would take, if I had different networks with different costs, it would take the network with the least cost and it would assign that to this summary advertisement. All right, did it work? Let's go to R1 and see. Did I summarize all of these 172.17 networks? Let's do a show IP route. Yep, sure did. 172.17.0.0/22. So summary address is what we use on the ASBR. Area range is what we use on the ABR. Our focus is mainly going to be on OSPF version 3 in this section. Before we get into OSPF version 3, let's talk about virtual links for a second. We talked about the fact that if we had more than one area in a network, one of those areas had to be area 0, that our backbone area, and it had to be numbered as either 0, or we said we could use dotted decimal. We could number it as a 0.0.0.0. What if we do have that company merger though, and we end up with something like this that we see on screen? We've got area 0 attached to area 1, and then attached to area 1, we've got area 0. Area 2's, or excuse me, we've got area 1 attached to area 2, and area 2 is not attached to area 0. That breaks the rules. That's not valid. We will not see a lot of those area 2 networks show up in area 0 if we do that. How do we fix it? Well, there is a workaround. It's not like a best practice. You shouldn't design your network with the anticipation of using these, but there's a fix, and it's a virtual link. Now, what that virtual link is going to do, it is going to virtually form a connection between, in this case, R2 and R3. So even though area 2 is not adjacent to area 1 or area 0, in other words, R3 does not have any interfaces in area 0, we can make it virtually have an interface in area 0 and therefore be adjacent. It's a virtual tunnel interface that we set up by setting up a virtual link. Now, when I say tunnel, you might get a little concerned because with a lot of our tunneling technologies like GRE, IPsec, yeah, it's not as efficient because we're adding on all this tunneling overhead. We add on a GRE header, or we do the encapsulating security payload with IPsec and we add on a big header. That's not a big deal here. With virtual links, only the routing updates themselves, like the hello messages, they're going over that virtual tunnel, but the actual data is not. The actual data does not get encapsulated. It's still just going from R3 to R2. It doesn't get extra headers, so we don't have to worry about the MTUs or anything like that. It's not too bad, actually. But there is a requirement that area that we're going through. Like if I'm going from area 2 over to area 0, I'm going through area 1. That's called a transit area. And there's a rule that says that transit area, it cannot be a stub area or any form of stub area that we've talked about. Let me show you the configuration real quick on screen. It's really simple. In router configuration mode, let's take R3 for example. I would say area 1 because I'm specifying the transit area, not the area that I'm trying to get to or the area where I'm coming from. You specify the transit area. You might want to write that down. A lot of people have trouble remembering that. But area 1, then we say virtual-link, and we specify the IP address on the far side. So I'm on R3, I'm going to specify the IP address of R2. It's loopback interface. Which is 2.2.2.2. I do the reciprocal thing on R2. I say area 1 because that's my transit link or transit area, and virtual-link 3.3.3.3. The IP address, the router ID, in fact, of R3. That's how you set up a virtual link. Now let's get in, and for most of the rest of the day, let's talk about OSPF version 3. Now again, to remind you, we said that OSPF version 2 would only route IP version 4 traffic. But in today's networks, we just might want to route some IP version 6 traffic. So how do we handle that? Well, there are a couple of ways that we can set up OSPF version 3. The first way, which I call the traditional configuration, is going to be essentially 2 separate configurations. One configuration is what we've already done. It is the OSPF version 2 configuration, and that's going to route our IPv4 traffic, and then we'll overlay that with an OSPF version 3 configuration that's going to route for IP version 6. It's like having 2 different OSPF instances running, one for version 2 and one for version 3. Let's set that up first, and then I'll show you a more efficient way. So let's go out to our live interface, and I'm going to bring up a different topology for us with some IPv6 addressing on it. Here we go. I still have our routers R1, R2, R3, but now we have some IPv6 and IPv4 addressing. And I need to move over to the correct router. So it's router R1 in this topology. And the first thing we have to do is just to set up regular OSPF version 2. That's going to do our IP version 4 routing. So I'll do this fairly quickly since I've already done it on 3 routers already today. And I won't take the time to fool with the reference bandwidth or the passive interfaces or anything like that, or the router ID. We've already talked about those. Let me just get it working because I really want to focus on version 3. So I'll say router OSPF, process ID 1, and as a shortcut, I'm going to say network is 0.0.0.0, 0.0.0.0, because I'm encompassing all interfaces that are up that have an IP address on R1. And I'm going to say, you all belong to area 0. And I'm done. Let's move to router R2. On router R2, router OSPF, process ID 1. I cannot do the network 0.0.0.0 trick here because I'm in different areas. So I'll say network 172.16.1.0, wildcard mask of 0.0.0.3, area 0. Network 192.168.1.0. That's my interface off of gig 0/2. And that's going to be a wildcard mask of 0.0.0.3. It's in area 1. Got to be careful to get those straight. Let's do the loopback interface. Network 2.2.2.2, 0.0.0.0. It's also in area 1. And I'm done on R2. And real quickly on R3, I'll say router OSPF 1. I'll do network 192.168.1.0, 0.0.0.3 is my wildcard mask. I'm in area 1. Network, I guess I could have done the all zeros thing here too as well. Network 3.3.3.3, wildcard mask of all zeros. You're in area 1. Okay, I think we're done. Oh, you know what? Let me do this. Let me prove something else here. This will lead us into our OSPF version 3 discussion. I'm going to go back. You know what? I'm just going to kill my process. I'll say no router OSPF 1. Let's just kill that altogether. It's gone. I'm going to say router OSPF 1, and I'm going to give just one network statement. Check this out. I haven't talked about this yet. I'll give just one network statement. 172.16.1. Let's see. No, 68. I knew that didn't look right. 172.168. No, it is 192. The font is really small on screen. 170. Yeah, it is 192. Excuse me. So it is 192.168.1.0, 0.0.0.3, area 1. But when I do the network for 10.2.2.0/24, I'm not going to give a network statement for that. You know, I could still use my loopback network statement, I suppose. That wouldn't hurt anything. I'll still say 3.3.3.3, 0.0.0.0, you're in area 1. Here's what I want to show you. I'm not giving a network statement for that gig 0/2 interface for network 10.2.2.0/24. How do I make it participate if I don't give a network statement? Well, we have the option with OSPF version 2 of going into the interface itself and saying, hey, I want you to participate in this routing process. I mean, after all, that's what the network statement's really doing at its essence. It's making interfaces participate. So I'm going to go into interface gig 0/2, and I'm going to say IP OSPF process ID 1. I want you to belong to area 1. So I told the interface explicitly, hey, I want you to be part of this process and I want you to belong to this area. That's another way that we can advertise a network. If I do a show IP route, let's see if I see everything. I want to make sure I've got full reachability. I'm not seeing 1.1.1.1. Oh, I'm not seeing anything actually. We got some troubleshooting to do here. All right, that's fine. I said we'll do some troubleshooting today. Let's do a show IP OSPF neighbor. I got no neighbors. Let's do a show run pipe to begin router. I'm just trying to make sure I didn't mistype something. 192.168. 1.2, that's area 1. Okay. Let me go check my config on. Oh, yeah. Here, I mistyped this. Typo, my bad. This should not have been 172.168. It should have been 192.168. Let me fix that. Router OSPF 1. This is on R2. Let's get rid of this command. Mistype that. Should have been 192, not 172. Okay. Hopefully that'll make things better. Let's give it a second. All right, I've got a neighbor. Show IP route. Can I see everything now? Ah, yes, I can. I can get all the way over to R1, looks like. Excellent. Oh, if I do a show IP protocols that I showed you earlier, it's going to show up a little bit different if I tell the interface itself to participate. Look at this. It says, yeah, I'm routing for these networks. I did that with a network statement, but then it says routing on interfaces, and this is the interface that I explicitly told to belong to that process. Okay, that's what we've already done. Nothing much new there. Now, let's add IP version 6 routing. And here's something that might come as a surprise to you if you've not worked with IPv6 routing. By default, our Cisco IRS routers, they do not support IPv6 routing by default. We have to turn it on. It's turned off by default. Interesting. So let's turn it on. I'm going to say IPv6 unicast routing. If I don't do that, we're not routing IPv6. IPv6 unicast routing. And something that I just personally like to do, I like to say IPv6 Ceph. That Cisco Express forwarding, that just makes the forwarding more efficient. Not required, just something I like to do. All right, we've got IPv6 enabled. Now, let's configure OSPF version 3 using the traditional approach. I'm going to say, instead of router OSPF 1, I'm going to say IPv6 router OSPF 1. And that 1 did not have to match, by the way, my OSPF version 2 config. I will set a router ID just to show you how we do it. I'll say router ID, let's see, 3.3.3.3. I could make a passive interface out of gig 0/2, I suppose. It's not going to another router. I'll say gig 0/2. You know what? Come to think of it, I can make a passive interface out of loopback 0. It's not going anywhere either. Let's stop with our router config right there. But wait, I haven't given a network statement. Here's the thing. We don't give network statements with OSPF version 3. We do all of it from interface configuration mode. So let's go into interface gig 0/1 and say IP version 6 OSPF. I want you to belong to process ID 1, and I want you to belong to area 1. Let's go into gig 0/2. Same thing. We're part of OSPF process ID 1 in area 1. Let's do our loopback. Loopback 0, IPv6, OSPF 1, area 1. I think we're done on R3. Let's go back over to R2. Here I have to be really careful because I'm spanning a couple of areas, but I'll try to do this one a bit more quicker. Since we've already talked about these commands, I'll say IPv6 unicast routing to enable that, IPv6 Ceph because I want to speed up my routing decisions, IPv6 router OSPF 1 to start the OSPF routing process. I'll give it a router ID of 2.2.2.2. I'm going to go into my interfaces and tell them to participate. Interface gigabit 0/1, that is in area 0. So I'll say IPv6, you're part of OSPF process ID 1, but you're in area 0. For interface gig 0/2, you're also part of OSPF process ID 1, but you're in area 1. And for our loopback interface, I'll say IPv6, process ID 1, area 1, and we're good to go there. With just one router to go. On R1, similar config. I'll say IPv6 unicast routing, IPv6 Cisco Express forwarding, IPv6 router OSPF 1. Router ID is going to be 1.1.1.1. I can make a passive interface out of gig 0/1 and also out of loopback 0 because it's not connecting to another router. We go into our individual interfaces and I'll say IPv6, you're part of process ID 1, you're in area 0, gig 0/2, process ID 1, you're also in area 0, and finally our loopback, you're in area 0. Nice. We are done now with the traditional configuration of OSPF version 3. You see what we've done? We've created two different OSPF processes. One, OSPF version 2, it's writing IP version 4, and one for OSPF version 3, and it's writing for IP version 6. So if I say, let's go to R3 for a second. Let's say show IPv6 OSPF neighbor. A lot of the show commands are identical to OSPF version 2, except instead of saying show IP OSPF, it's show IPv6 OSPF. Do I have a neighbor? I do. Awesome. Let's say, let me look at an interface. I'll say show IPv6 OSPF interface gig 0/1. It shows me the link local address that I'm using with IPv6. It's a broadcast network type. There's my router ID. Similar information to what we got before. Now, let's look at the database. Here's where some of those new LSA types show up finally. Let's do a show IPv6 OSPF database. We still have type 1 LSAs, router LSAs. We still have type 2 LSAs, network LSAs. Oh, and instead of calling them summary LSAs, which I really, really disliked, finally, OSPF version 3 no longer calls type 3 LSAs summary LSAs. They say they're inter-area prefix LSAs, which is exactly what they are. I love the new naming system they've given us there. Let's scroll down to, we've got some type 8. You see we've got type 8 LSAs. These type 8 LSAs, they give us information about the IPv6 addresses on a link, including link local addresses, as we talked about earlier. Let's see. This, even though it doesn't say type 9, these are type 9 LSAs, the intra-area prefix links. This contains prefixes for stub and transit networks. This information is only sent within an area. Let's take a look at our IPv6 routes. I'll say show IPv6 route. Notice that some of these have the OI flag. That's OSPF inter-area. We still see, we learned one within our area. That's our loopback interface from R2. So instead of just looking at the IPv4 routing table, we just say show IPv6 route. All right, that's the traditional way of doing it. Now let's use a new and improved version. It's called the address families approach. And to demonstrate this, I need to get rid of what we just did. I need to kind of blow away our traditional configuration. Let me do that really quickly. I'll go to router R1 and say, no, router, OSPF 1. No, router. Actually, no IPv6 router. OSPF 1. Okay, got rid of OSPF on that router. Let's do it for R2. I'll say no, router, OSPF 1. No IPv6 router. OSPF 1. And we're done there. One more to go. We'll say no router, OSPF 1, and no IPv6 router, OSPF 1. All right, now let's set, by the way, we would still have to go in and say turn on unicast routing. That's just to enable IPv6 routing, period. But we've already done that. We won't get rid of that. Now let's configure the address families approach. I think you're going to like this. I'm going to say router, different syntax here. I'm not saying IPv6 router. I'm saying router OSPF v3 for version 3. And I give a process ID. And here, I can give a bunch of commands. For example, let's just give the router ID. I'll say that the router ID, I'll say router-ID is 1.1.1. Actually, I'm R3. 3.3.3.3 is going to be my router ID. Now, that's going to apply to both IP version 4 and to IP version 6. I've got a passive interface, don't I? I could say, with my passive interface, let's see, gigabit 0/2 could be passive. So I'll say passive interface gig 0/2. Now, let's create those address families. I'll say address hyphen family IPv4. I also want to set up an address family for IPv6. So address family IPv6. Now, I just need to go to those interfaces. Because I've already said, hey, I want you to do IPv4 routing, and hey, I want you to do IPv6 routing. Now, let's go to the interfaces and say, yeah, I want to belong to both of those guys. So let's go into interface gig 0/1, and I'll say OSPF v3. See the different syntax? Process ID 1. For the IP version 4 address family, I want to belong to area 1. For the IPv6 address family, I also want to belong to area 1. For interface gigabit 0/2, same thing. I want to belong to area 1 for both of those address families. Same thing for the loopback interface. Loopback 0. I want to belong to both of those address families. Let's configure router R2 now. On router R2, I'll say router OSPF v3 process ID 1. We'll say the router ID is 2.2.2.2. That gets inherited by the address families. Now, by the way, if I go into an address family like for IPv4, what if I said at that point, oh, really, I want the router ID to be 2.1.1.1? Which one wins? I've got conflicting information. The more specific configuration wins. So the IPv4 address family, that would beat out this thing that I've configured globally for both address families. No passive interface here, so let's just create the address families. I'll say address family IPv4, address family IPv6, and then we go right to the interfaces and say, I want you to belong to both of them. OSPF v3, process ID 1, IP version 4 address family, you belong to area 0. I want to make sure that's correct. That's gig 0/1. Yes, that looks good. Also, for IP version 6, same thing. Let's go into interface gigabit 0/2. These are going to belong to area 1. And our loopback interface, they're also going to belong to area 1. And we're done on R2. Just one router to go now. On router R1, we'll say router OSPF v3 process ID 1, and I'll say router -ID is 1.1.1.1. I've got opportunities for a couple of passive interfaces, gigabit 0/1 and my loopback interface. Oh, typo there. Now let's go into the interfaces and say, I want you to belong to those address families. Interface gigabit 0/1 is going to be OSPF version 3 process ID 1. For the IPv4 address family, area 0. For the IPv6 address family, area 0. Gig 0/2. Same thing, same address families. Belong. One more to go. Interface, loopback 0, OSPF version 3, process ID 1, IPv4 address family, IPv6 address family, and once again, we are done with our configuration. It worked a little bit differently, didn't it? We could set passive interfaces just one time, and they would be inherited down to our address families. The verification commands are also a bit different. Let me go over to router R3 again, and let's do a show OSPF version 3 neighbor. Instead of saying show IPv6 OSPF neighbor, it's show OSPF version 3 neighbor. And notice it shows me my neighbor for IPv4 and my neighbor for IPv6. Let's take a look at the database. Show OSPF version 3 database to see our link state database. And here we see our link state database for IP version 4. And notice that even though we're talking about IP version 4, because it is OSPF version 3, they still don't call the type 3 LSAs the summary LSAs. They use the much improved name of inter-area prefix. I love that. Let's see. To look at the routes, I can say show IPv6 route. Can I see throughout the network? Yeah, sure can. All that looks good. Any other? No, I think that's enough configuration command or enough verification commands. And I've got just one more demo for you before we wrap things up today, and that is authentication. We'll just stay here in the live interface and we use the same topology, but let's build on this OSPF version 3 configuration. Now, we can set up authentication with with OSPF version 3, but OSPF version 3 gives us enhanced security. So I thought I'd show you the OSPF version 3 way of doing it, but it's very similar either way. Here's the deal. When we set up OSPF authentication, we can set it up just between two routers, like between R2 and R3, and I'll do that. Or we could set it up for an entire area. like area 0, and I'll do that as well. But let's go to R2 to begin with, and let's set up authentication between R2 and R3, just on that link. Again, what we're trying to prevent some rogue actor from coming in and connecting their rogue router into the network somehow. Wow, Alexa just started talking to me for no apparent reason. Not sure what I said to trigger that. But what was I saying? Oh, yeah, we've got the link between R2 and R3, and we're trying to prevent somebody from adding their own router and forming neighborships and corrupting our OSPF database. So authentication in an enterprise environment, really, really good practice to do. So here's how we do it. I'm going to say in interface gigabit 0/2, because that's the link that I'm going to authenticate over, I'm going to say OSPF version 3 authentication. Now I've got options. I could say I don't want to do authentication at all. I could say no. I could use a keychain. That's something you oftentimes see with EIGRP authentication, where you can have different keys that have different key lifetimes. So one key is not going to be valid forever. It's going to go to a different key with a different start and end date. You could do that all that here. I love IPsec though. I'm going to use IPsec, IP security. Very, very secure. I'm going to say IPsec, and it says, you need to give me a security parameters index. What in the world is that? Well, that's just a number that is specifying the parameters we're using, like what kind of hashing are we using. It has to match at the other end, basically. I'll just say it's an SPI of 1, and it'll just need to be 1 at the other side. Actually, 1's not about. I think it has to be in increments of something. Oh yeah, it has to start at 256. I knew something was different with that. Yeah, we're going to start at 256, and then I'm going to say I want to use SHA-251, or rather SHA-1 hashing, and I'm going to put in a hex string. It's 40 characters, my SHA-1 key. Now, this is not going to be a key that I would want you to use in production, but just to make sure I type it correctly on both sides, it's got to be 40 characters long. So what I'm going to do is type 0 through 9 4 times. You ready for this? I'm going to say 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Let's do it again. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Halfway there. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. One more time. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. I hope I did that right. And we'll do the same thing on the other side in just a moment. But I've added that big string, and we're done on R2. Let's go add a matching string on R3. On R3, I'll go into the other end of this link, interface gig 0/1, and I'll say OSPF version 3 authentication. I'm using IPsec. I'll give that same SPI of 256, and my SHA-1 key is going to be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4. I think that's right. I'll enter that, and let's just confirm that we are still neighbors with R2. I'll say show OSPF version 3 neighbors, and let's see if I am still a neighbor. And I am. That's great. I can say show IPv6 OSPF interface gig 0/1. Let's see if it'll tell us anything about authentication there. I thought it might. I'm not sure. Include authentication. Yeah, it does. It says, yeah, we're doing SHA-1 authentication. My SPI is 256, and we're up. So that's how we can verify it. Now, let's take a look at, this will be our final demo of the day. Let's take a look at how we can set up authentication within an area. We'll do it within area 0. So I'll go to R1, and on R1, actually, I'll start on R2. On R2, I'll say router OSPF version 3, process ID 1, and I want to apply authentication. So I'm going into router configuration mode, not interface configuration mode this time, because this is for the entire area. I'm going to say for area 0, I want to set up authentication. My SPI has to be different, has to be unique. It cannot be 256. I'll make it 512. And my SHA-1 key is, you guessed it, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Oh, I tried to do that in one breath. That was difficult. All right. Oh, I had a typo. What was that? I said authentication. Oh, I forgot to say IPsec. My bad. Let me fix that. Authentication, IPsec. There we go. And let's do the same command on R1, the only other member of Area 0. I'll say router, OSPF version 3, process ID 1, Area 0. That's what we're a member of. Authentication, IPsec. I remember to say that this time. My SPI is 512, I think. And my SHA-1 key is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. All right, let's press enter. Hopefully I got those correct. Let's see if I did. Do I still have a neighborship with R2? Let's do a show OSPF version 3, process ID 1, neighbor? Yes, I'm still a neighbor. Am I doing authentication? Let's confirm I'm doing authentication. I'm going to say show IP. Let's go to R2 because it's got a couple of different authentications going. I'll say show IPv6 OSPF interface pipe to include authentication. Yeah. And we see here's our authentication for that link. And here's our authentication for the area. Now, that all looks good. It says we're doing authentication, but how do we really know? I mean, come on. Can you prove to me that we're really doing encryption? Yes, we can prove that because we're using IPsec. I can say, here's an IPsec command, show crypto. If I could spell, that would be super helpful. Show crypto, IPsec, Security Association for interface gigabit 0/1. And it says the number of packets that have been encrypted, the number of packets that have been decrypted. That, my friends, gives me assurance that we are really doing authentication within that area. Hope you enjoyed that demonstration. And let me click through these slides because we just stayed live through all that. And that's going to wrap up part 3 of our session today.